So today I want to talk about, I guess, a classification algorithm that I came up um, with Diane and James and Adele. Um, so this is just a novel classification algorithm that's based on a population of hypergraphs. So before I get into sort of the hypergraphy stuff, we need to talk about, I guess, what a classification algorithm is trying to do. And first of all, the classification algorithm that I'm doing today is a supervised learning sort of process. So we use a set of training data, and that'll sort of teach the model so that where we can take an unseen or an unknown piece of data and then classify that into a certain sort of category. So our training set just involves a bunch of data, um, and it has those sort of features that describe each piece of data, and we have the correct outputs. And so, like I said, this classification algorithm looks to categorize those unknown data sets, unknown data pieces into, I guess, unique classes. So the data set that I'm going to be working with today is based on some starch grains. And so this is sort of all the different species of grains that I'm going to be working with. So we have 7 different classes and they have varying numbers, but about, between 100 and 160 odd different pieces of data there. And so for each of one of these starch grains, I have 16 different features. And so these vary between length, area, perimeter, circularity, island position, and some Fourier coefficients, which were sort of calculated in a different study. So I'm sort of bringing all that information in to describe each one of these grains here. So I guess what we can do with all this information is we can put it all into an array or a matrix. So we have each row corresponds to a single starch grain. So we have a total of 944 here, and each column represents a particular feature. And so each entry in here is just a number, right? And in particular, it's a normalized measurement for that feature. So just go ahead and normalize each column, make sure the mean is 0 and the standard deviation is 1. And each entry just gives me, for example, this first column here just gives me the length, and in fact, the normalized length of each grain that I'm dealing with. And so this is a pretty standard setup that I think a lot of data sets can be made into when you have, I guess, observations and features. So just a quick reminder, but I'm jumping on the bandwagon of hypergraphs from Sarah here. So we know what a hypergraph is. It's just a set of vertices and a set of hyperedges. And these are what sort of, a basic hypergraph looks like. And the benefit of using hypergraphs in something like this classification algorithm, we'll sort of see the benefits a little bit later. But what the main sort of point is that we can not only, I guess, capture multi-way interactions. So for example, this green hyperedge here has 4 vertices, whereas if we were just playing in the graph theory world, we're really limited to edges that can only connect 2 vertices. So this gives us a lot more freedom, and we can capture a lot more information. So the other thing that I'll be talking about today is the incidence matrix. So just a reminder, this is just an array here with vertices as rows and the hyperedges as columns, and you basically just get a 1 in the entry if that vertex is within that edge. So if we find vertex 1 here, we see that it's in edge number 4, this red edge, and you can see that there's a 1 in this entry here. And this will be sort of critical as I go through the talk. Okay, so without going on too much, what I really wanted to do with this classification algorithm is classify units and in fact starch grains into classes or species using the features. So to do this, the method that I'll be running through today will be, first of all, I want to discretize my data set. So that will be allow me to sort of have a nice hypergraph with just ones and zeros in it, more or less. And then I'll be able to create that hypergraph model, which will then enable multi-way interactions. And then to increase, I guess, accuracy and performance, I'll be using a population of hypergraph models. So for the remainder of this talk until the end when I discuss some results, I'll sort of give this in a general form where I have N units, M features, and C classes. So this sort of algorithm can be used, I guess, for any sort of data set. So yeah, we start with what I brought up before, where I have each row as a starch grain, or you can think of these as any sort of observations or data pieces you have, and the columns represent the features. So we have the M features here, and this is sort of where we start. So my first problem that I needed to solve was that each entry in here is a real number, so ranging between negative infinity and infinity. And I want to discretize those, so I just want to get these to the integers. So what I can do is I can sort of create some sort of partition given some arbitrary values, L and alpha, that is up to the user. You can pick L and alpha accordingly. I'll mention that a little bit later on as well. But this partition here just gives me a bunch of partitions, each associated with the t value. And so that t value sort of indicates what interval it's in. So then I can sort of transform this F matrix up here to what I'm going to call this D matrix here, which is just going to be a bunch of integers. And it's going to really give me what interval each entry is from. And so another variable that I'll throw in here is tau. And that's just the maximum t across all my features. That way I have some sort of upper limit that I'm working with. Okay, so then now that we've discretized our data, we really want to create some sort of hypergraph. And in doing so, I'm going to create the incidence matrix, since it's probably the easiest thing to work with. And it comes down to this sort of formula here, which looks pretty gross, but it's probably easier just to look visually at what sort of this incidence matrix looks like. So we still have the rows as each of our data units, and each column really represents one of those intervals that I talked about before. So, and then we have this block matrix for each feature. So we have this really big matrix that's quite intense, but really each row, well, I guess more specifically, each entry will just have a 1 or a 0 in it. And it'll be a 1, for example, when, let's call this data unit 1 is in interval 1, there'll be a 1 here, and the remainder of this little section here will be 0. And then it'll go on, there'll be a 1 somewhere along here corresponding to where that feature lands in what interval. And so we have this incidence matrix here, which really looks at a hypergraph where the vertices are your data units, and then each interval for each feature is actually a hyperedge. So there's quite a lot going on. But I'm not quite interested in each of these individual sort of data units. What I'm actually really interested in is what class they belong to. So if I go along each sort of hyperedge in here, or each column, I want to find out how many from each class there are. So that's all that this formula here is doing. And I get sort of a more compact version of B through here. So I get still all my different types of hyperedges as my rows now. And you can see that we have tau m of them. So that corresponds with the tau times the m different features. And so each column corresponds to a different class. And so I just get, I guess, the numerical value or the proportion of that class which appears in that particular hyperedge. And then we go ahead and we want to normalize that. So then each row sums to 1. And so we can then consider each row as a probability distribution, right? So we can now sort of attach a probability distribution to each hyperedge. So each hyperedge, there might be all of the vertices contained within that hyperedge might be all from the same class, right? And so that sort of helps me understand that if I take some unknown piece of data, then I can sort of realize that if it hits that hyperedge, then it's pretty likely that that unknown piece of data corresponds to that specific class or species. Okay, so this W is sort of the basis of what we've created here from our hypergraph model. And just a reminder, I guess, is that we just created this W based on a particular L and alpha value. So now I'm going to talk about how I guess I take and I predict an unknown piece of data. So suppose we've gone ahead, we've got all our training data, and we've just done what I just spoke about. So we create this W, and we have some sort of normalized and discretized version of an unlabeled unit, a V1 up to VM. So how do I go? So I take my W matrix that I've just constructed here, and what I can do is that I can go across and I can take V1, for example, and that's going to correspond to exactly one of these rows in this sort of first block here. And in fact, it's just going to be a probability distribution, right? And what I can do is I can then drag that row into this V matrix here. And I can go ahead and do that for all my features. So I'm just taking the corresponding row in which this unlabeled unit hits each bit of the block matrix for all M features. Okay, so then I have a bunch of probability distributions, and there's a couple of different ways, I guess, I could sort of determine a class based on this matrix here. But I guess the more simple is just averaging them all out and then taking the maximum. So averaging each column gives me this vector here, and then taking the maximum version of that will predict a class for that unlabeled unit. So that's basically how I go from modeling all the way to prediction. But I really haven't utilized, I guess, the best part of the hypergraph. And I guess before that, back to this L and alpha that I talked about. So that was just based on one L and alpha value. What we can really do is we can vary L and alpha, picking as many different variations of those parameters as we want, and we get a population of hypergraph models, and then you get a bunch of different predictions or class predictions, and then you can write those all in a vector, and then again take the most occurring class, and that can be your choice of prediction for your unlabeled unit. And so what this does is I guess it reduces the bias on L and alpha, and you can do this as many times as you want to get as much robustness or accuracy as you like. And if I just do this so far, what I'm going to do is call this the H1 algorithm. And I just do that because this one just sort of means that I haven't really considered, I guess, pairwise feature interactions. I really only considered each feature individually. So now I can utilize, I guess, the benefit of a hypergraph, and I want to consider maybe two-way interactions among the features, knowing that's, maybe two features interact within each other. And even more generally, I want to think about eta-way interactions. So thinking about 3, 4, 5, and so on interactions. So can we generalize this so we consider all the different interactions these features could possibly have? So if I consider the hypergraph that I had beforehand, which is just this first part here, so I have my normal vertex set, which are just my data units, and each edge is, or each hyperedge is really just corresponding to one of those intervals for each feature. So I have tau m of them, so just listed here. Well, so if I want to consider a two-way interaction, well, then I came up with this thing called the two intersection hypergraph. And so this is quite a bit of a handful down here again with the notation. But what I do is I pretty much take two hyperedges from up here, and I pretty much look at the intersection of those. So maybe I consider, length from interval 1, and I take circularity of interval 2. I look at that intersection, and that forms a new hyperedge. So that's two particular bits of information combining there, something like length and circularity at a particular interval, and sort of looking at what classes of my data units fall into there. And so we can sort of generalize this notation and this definition here to 3 intersection hypergraphs, 4, 5, and so on. And we can pretty much create an incidence matrix quite easily from the first one that I've created beforehand that I constructed just with some linear algebra, but I'll leave that to the side today. But it is quite straightforward. So I'll talk about some results now. So what I did on that original data set on starch grains with my 944 starch grains, as I took a training set and I created a bunch of hypergraph models, and then I left some data to the side that I wanted to test and see if I could get that right. So my L and alpha, I just picked them at random. These values just so happen to work for me. They're nothing unique or special about them. Um, so this is the main result of the discussion today is basically what I wanted to do and what I strive to do in this classification algorithm is that I wanted to beat the random forest, the very stock standard thing that you'd get out of a MATLAB or R package. And you can see that the accuracy score here is about 0.55 or 55%. So I wanted to try and get something better than that. And so when I did the H1 algorithm down in the green here, you can see that it doesn't work very well. Um, and I guess we have an accuracy score, and we also have the population of hypergraph models that we constructed from 250 up to 2000. And you can see that as we go across, even just with this H1 algorithm, we get a little bit better accuracy as we go along, but it's far beneath the random forest. And this is where the H2 and H3s, so considering 2 and 3-way interactions between the features, we get a slightly better score, especially when we do 250 hypergraphs in our population. But as we increase our population size, we get an even better accuracy as we go along. And you can see that we end up, the H3 score gets close to 56% accuracy, which beats out the random forest by not a lot, but considering the difficulty of this classification problem, it was quite an improvement. And you can see here that if you went to the 4-way interactions, which I didn't look at just for time's sake, you'll probably get it even better, but you'll probably hit some threshold eventually on, I can't imagine looking at 15-way interactions between 16 features would be useful. But I imagine eventually you'd hit some upper threshold on the number of interactions which are useful. So the other bit of information the other result I wanted to talk about is on this x-axis here, what I have is a threshold. So if we think about how I classified each data unit for example, I took 2,000 different hypergraphs, and each individual hypergraph would give me a prediction. So if I set some threshold and say that in order to classify one of my unlabeled or unknown data units, I want 95% of my 2,000 hypergraphs to agree, then I get an increase of up to close to 80% accuracy. And you can see here another point to make is that the 2-way interactions outperform the 1-way interactions. So that's a nice result as well there for, I guess, the use of hypergraphs and their ability to model 2, 3, and 4-way interactions. All right, so just a quick summary. I guess the aim of the study here was to classify starch grains into species using the features. And I guess the benefit of what I've done today and shown you is that given a random data set with a similar sort of, I guess, setup, is that we can classify units into classes using features. And so what we showed here today is that we needed the discretization at the start in order to simplify, I guess, the model to start with. And this really enabled a hypergraph framework. And then the hypergraph models that I discussed today were able to capture multi-way interactions, which you saw improved on each other as you went through the 1, 2, and 3-way interactions. And then the population of hypergraphs, well, that just increased performance, but it also increased robustness, right? So less bias on your alpha and L values that you picked. And I guess the main results that were nice to see out of this study was that we improved on the benchmark algorithm that we set out to beat, which was the out-of-the-box random forest. And then we're also robust to feature selection using the 2 and 3-way interactions. So yeah, that's all I had to say for today. So thanks everybody for listening.